Welcome. I'm just going to do a quick demo showing how you can use memory mapping in C. So as usual, I like my virtual hikes at the beginning. I'll probably be using this one for a little while just because it took a little bit of time over the weekend just to figure out how to use the Unreal Engine. But I'm always curious. I find it really interesting in terms of what we take from operating systems. Just gives us a little bit more patience to work with really complex systems like Unreal Engine. Let's look at the code first. I've got quite a bit of comments. So when I post this code, you can take a look at them and you can get it a little bit more detail. If you look at the headers, you're probably familiar with some of the other ones that I've used up to this point, except the only new one would be system/memory management header file. So mman.h. This one just gives us some of the preprocessor defines inside that header, or the constants that we might use for configuration of memory mapping that you can see down in the function call right here. So this is one of the system calls we looked at. I think last week we saw it at the beginning of chapter 10, or the first half of chapter 10. And the issue with this one is that when you want to use it for anonymous memory maps, so there is no backing file, there's nothing on your disk backing up this memory that you're mapping in RAM. But once you map it, then you could potentially share it with another process. Now, the issue here that I wanted to point out and emphasize is that I don't have a separate exec call. I'm only going to do a fork. So we've got the two if blocks. The first one is for the parent branch code, and then the second one is for the child branch code. So we'll have all of our code inside this one file. And if you really want to, you can separate it into multiple source code files, and then keep it a little bit more organized that way if you're going to write a larger project. But for demonstration purposes, by this point, I hope you're very comfortable with the fork call. And when we go to look at the child branch, again, we're not doing any exec call. We're just writing the code that's going to execute in the child. So the reason I have it this way is because when you go to do the memory map, it's really the only way you can set it up like this is if you've got a child process that hasn't been overwritten by an exec call. So it allows you to do the anonymous sharing of memory between the parent and the child processes. And I tried last semester setting it up so that you might be able to do an exec call and maybe have a completely separate process try to share that memory. None of the configurations I tried seemed to work, and I couldn't find anything online in the documentation anywhere about that being possible. And thinking about it a little bit more, and after trying to set that up, maybe the reason is because it would be a security risk if you allowed that to be possible. I think you probably have a lot more security issues if you could just take any kind of execution of other code and start sharing the same kind of memory that's anonymous that way, that's not backed up by a file. Now, I'm not an expert in security, and that's not my specialty. So I'm kind of guessing there a little bit. Nevertheless, I've got this example code for you. The configuration here works. And then the only thing I'm actually calculating as far as what this code does is just a demonstration of calculating Fibonacci numbers. So I always like to do that because when you look at the function call for Fibonacci, it's always a good reminder of recursive functions where the Fibonacci function is turning around and calling itself again twice. So I usually like to have it somewhere in a class where we're doing some kind of programming, just to remind you of it. You're doing your recursive function calls for sorting with merge sort. So I think it is good to see it in a slightly different use. Okay, some of the other things that are set up here, you can see we've got to know on our system, these two constants that I have for these macros, we have to know what our page size is on our system because we have to use that as part of the configuration for memory map. And then we're going to specify how many of those pages we would like to set up to be mapped. So in order to get this number, you've got to do on command line, just find out what is the actual page size. So get conf will give that to you with an environment variable page size. Let's see. And for me, it should be the same number that I had when I was using a virtual machine, but it might be different on your system. We never know. So for me, it's set up for 4K on my WSL with Debian Linux. And so that's the number I'm going to put for my define there. So 4096, so 4K. And I'm going to do 2 pages just to show you that you can have more than one. Then setting up the data that I would like, I'm keeping myself organized by creating a struct. I'm doing a type define so that way I can be cleaner with setting up that as a variable for that type. And within it, I've got some dynamically allocated memory map, and we want the address to be passed there. And the number of bytes for the memory address, I need to use long as a data type, not int. And that's specific to my system. You're likely going to have the same thing. So maybe more than 4 bytes for the memory address you might need. Okay, and then what number of Fibonacci would I like to calculate? Which number in the sequence? So I want to be able to store that and pass it. Let the child work with it. You can see that I'm using those as the second parameter to say how much memory I'd like to map. It's got to be some multiple of the number of pages. So that's why I've got the other macro to multiply. Because this is anonymous memory, I'm not specifying which memory address location. So I'm going to let the system decide that for me rather than passing in a specific memory address location. And then the next 2 parameters, or sorry, the next parameter is a combination with a bitwise operator. It's doing an OR to combine the configuration options that I want to both read and write from this memory. And then the next parameter is going to be to decide what kind of memory this is going to be. It's going to be shared. So that way, when I create the child process, it will have access. And this is going to be anonymous memory. It's not going to be associated with a file on disk for backing. If we think about what's going on with virtual memory and when you can swap things in and out of virtual memory. The next couple parameters, -1, is because there is no file associated with this memory. It's anonymous, so there's no file descriptor. And then of course, because I want to start using it from the very beginning of this memory, there's the 2 pages that I would like to work with, and I want to work with the very beginning address, so I don't have any offset, and the offset is just set to 0. Okay, I've got some output just to show that we've got results for a memory address, and then if there's any kind of errors, we might get an error statement. We set up the data that I would like to pass to the child. On the first assignment, you were not allowed to use things like string to L, I think. No, I think it was another function. I didn't want you to use string tokenizer because that does quite a bit in the background. And it can be a little bit tricky to know exactly what's going on with that function in the C library. But you've got other C library functions like string to long. Now, when people look up in C how they would like to convert a string to a number, they typically tend to go with A to I. But something that's a little bit more up to date would be string to L. So we pass this as an argument. So I've designed my program so that the next value you type after the execution name of the program, it will go in as the first argument. And I'm going to store it in with my data. Okay, the child process, I'm going to pass these values so it can work with them. It's going to do its thing. It's going to do the fork when we create child process. Once it's finished, we have the parent wait until the child finishes executing. So let's go take a quick short look at that. I'm not sure if I've demonstrated code that uses wait PID yet or not. This function will allow the child process to execute. So the parent process is going to stop execution here. It will block until the child finishes execution, and then we get back a status value depending on whether the child executed successfully. And we can observe that value that was passed back. The else block, if it didn't call back with a value of -1, then there was some kind of problem with the child process, and we might get a little bit more detail by observing the value that was passed back in status. So that will be the lower 8 bits of the status value. So this is what W exit status is doing. It's helping you interpret those lower 8 bits. The child process could be designed to pass back some number. Here I'm just doing exit 0, but you might pass back a different value other than 0 to indicate some kind of error that you could get back through this observation. So it's up to you in the design of your child code to interpret what that number will mean. A trick you could do is that you might have different exit cases with different numbers. And you might play this game of setting different perfect values of 2, powers of 2, to then combine them together to maybe specify multiple things that are an issue. So you could do a little bit of your own error programming there if you wanted to get more sophisticated. But this is just a really simple example, and it's just giving back status value of 0 and then anything else. I don't have any other cases set up in here other than just to calculate the Fibonacci numbers. Okay, so that's roughly what's going on in this code. I'm going to go ahead and execute it. There's a little bit more error programming. If you want to just take a look at that later, you could play around and look at some of the other error codes in the documentation if you wanted to practice on your own further. Ultimately, what this example is doing for you is getting you an idea of how to start working with memory maps and multiple processes. Let's see. I've already compiled it. You don't need to use any special options like linking with pthread library. So it's like a typical GCC daemon.c daemon. And then of course, what value of Fibonacci number would I like to calculate? So I'm going to try to do up to, I think, 42. Maybe I'll do up to 45 and we'll see how long it takes because it starts to go slower. There's a limit to how much recursion you can do on a system because it takes time. So we've got the child process executing. Of course, I've slowed it down a little bit with my calls to nanosleep. So you can see up to 45, it's starting to take quite a bit more time. And then I kind of wonder about those last few numbers, because when you get a lot of digits, if we're using an integer data type, we might have to start worrying about an error where you have integer overflow, and then the numbers no longer represent the actual value because you can't store them in the number of bits that are possible with 32-bit integer. And it might wrap around to negative values, or it might even skip those negative values and then start going into lower integer values that are not the actual Fibonacci number you would want. If you wanted to calculate any values that are further along in the sequence, you'd probably want to specify another data type like long so that you can store the correct values without any integer overflow. So you got to be careful there when you start doing computations that are a bit more intensive. Obviously, even if I wasn't doing calls to nanosleep, you'd get to a point in the sequence where even if we were trying to do it as fast as possible, it still would take too long. So what you'd really want to do with Fibonacci numbers instead, if you were wanting them inside your program, other than just as a trivial example like this, you'd want to use the function that just calculates them right away rather than calculating them recursively. If you're curious about that, you can always talk to me about it. Otherwise, this is a pretty short demonstration. I think that's about all we need to talk about here. If you've got any questions, you're very welcome to ask me about it. And there's a link to the reference that can get you into a little bit more detail about memory mapping.